Hello everybody, my name is Michael Scholz and I'm a researcher from the Technology Campus in Grafenau, which is a campus that belongs to the Deggendorf Institute of Technology. Today I want to present some insights from a research project we conducted in cooperation with a partner from the steel industry. Our partner wants to get a step closer to a so-called eco-efficient factory for zero. But what is eco-efficiency and what is a factory for zero? And last but not least, how can we combine these two concepts? Eco-efficiency is typically defined as the quotient of an economic value and an ecologic footprint. So if we can create more products while using fewer resources, we have improved our eco-efficiency. And on the other side, a factory for zero consists of production facilities that can intercooperate without some human intervention. So at the end, we have interconnected and intelligent production devices in our factory for zero. And it is this intelligence that makes the connection to what we call eco-efficiency. Intelligence can be implemented in some algorithms that allow us to use fewer resources while producing automatically our products. In this project, we focus on the process step of cutting steel. Cutting steel can be done by automated robots. But to be eco-efficient, these robots need to ensure that they produce as less as possible waste. Thus, it is of utmost importance that these robots have implemented some intelligence that first plans the cutting layout such that this cutting layout ensures to save as much as possible waste. Planning cutting layouts falls into the category of bin packing problems which are in P hard. In our case, we want to cut out rings from rectangular bins. And these rings are of different inner and outer circles. So we have small rings, but on the other side, we also have very large rings. And the same holds for the bins. We consider bins of different sizes. And this makes it extremely hard to find a solution, especially if we need to consider hundreds of different ring sizes. To be more specific, we want to find out which rings we should cut out from which bins in order to be eco-efficient, or in other words, in order to save as much as possible waste. Because our rings are of different inner and outer circles, we can stack rings into each other. Therefore, we have a so-called nested problem that consists of first stacking rings into each other and then placing these ring hierarchies on our rectangular bins. We want to achieve two research goals in our project. First, we want to develop an algorithm that estimates cutting layouts which aim at minimizing waste. This algorithm also has to be fast enough to be used for daily production planning. Or, in other words, it has to be fast enough to be used to automatize the process step of cutting out rings from rectangular bins. This automation allows us to achieve the overarching goal of getting a step closer to a factory for 0. The second research goal is to evaluate the algorithm with regard to waste reduction and computation time. Waste reduction corresponds to the overarching goal of having an eco-efficient process. So our algorithm should enable us to get a step closer to a so-called eco-efficient factory for 0 by reducing waste as much as possible, and on the other side being as fast as possible so that we indeed can automatize the process step of cutting out rings. The problem of stacking and packing rings into rectangular bins can be divided into 3 sub-problems. For each sub-problem, we propose an algorithm. The first sub-problem is to determine a set of ring hierarchies with a minimal sum of top-level radii. In other words, we want to identify rings that can be stacked into each other. In order to achieve the goal of minimizing waste, these ring hierarchies should have top-level rings with an outer radius that is as small as possible. And furthermore, we want to have as less as possible of these ring hierarchies. Once we have identified an optimal set of ring hierarchies, we place all of these ring hierarchies onto all of our bins. Or in other words, we, in the second subproblem, identify all possible combinations of ring hierarchies and bins. These possible cutting layouts are the basis for our third subproblem, in which we want to select the waste minimal cut layouts. This can be done by a linear programming solver. Each of these subproblems is so hard to solve that it is not possible to come up with an exact solution within a couple of years if we consider hundreds of different ring sizes. We therefore need to relax our problem and define some assumptions for the solution. The first assumption or relaxation is that there is exactly one ring at each hierarchy level. Or in other words, we stack one or no ring into another ring. Once we have defined our ring hierarchies, we place them on the possible bins in order to generate all possible cutting layouts. And for that step, we define our second assumption, that is, we approximate our ring hierarchies by squares. And finally, our third assumption is that once we have placed one of the ring hierarchies on one of our available bins, we approximate the remaining space by several rectangulars that can be used in the next iteration as a bin on which some other ring hierarchies need to be placed. Based on these relaxations, we implemented algorithms for each subproblem. We used these algorithms to conduct some first computational experiments. In each experiment, we either used 10, 25, or 50 different ring sizes, or in other words, different outer circle radii. Each outer circle radius is drawn from a uniform distribution between 250 and 750 millimeters. The number of rings is drawn from a truncated normal distribution with a mean of 100 millimeters and a standard deviation of also 100. The minimal number of rings per ring size is 50, whereas the maximal number of rings per ring size is 500. The bins we used in our computational experiments are given in this table. Their length is between 1000 and 3000 millimeters, whereas their width is between 500 and 2000 millimeters. And as you can see in this table, the rectangular bins number 6 and 7 are squares as a special kind of rectangulars. The results of our computational experiments are presented on this slide. In total, we conducted experiments in 9 scenarios. Each scenario is different in the number of used ring sizes and the used bins. We run 100 experiments per scenario, and the first scenario, for example, used 10 different ring sizes and bins number 1, 2, and 3. On average, we generated more than 1,500 rings for this first scenario. The number of extracted possible cutting layouts is more than 28 on average. You can also see that our algorithms come up with a solution for this first scenario in only 0.05 seconds. On average, we wasted more than 83% of the bin area. This looks very high, but if we consider packing 2 rings with an outer radius of 500 millimeters into a bin with 2000 times 1000 millimeters, we can see that in this case we need to waste more than 92% of the bin area. As you can see in this table, the higher the number of used ring sizes, the lower is the wastage. And you can also see that in the case that we have 50 different ring sizes and we also have all 7 of our bins, our algorithm comes up with a solution in approximately 1 minute. Therefore, our algorithm can reduce the waste. It does not guarantee to find the optimum, but it comes up with a solution in only a couple of seconds, or if the instances grow, within a couple of minutes. To conclude my presentation, I want to present some practical implications. We can apply our algorithm to identify eco-efficient bins. For a given bin set a company is using, we can use our algorithms to identify satisfying cutting layouts and based on them to estimate the wastage. In a second step, we can add a new bin to this bin set or remove an existing bin and then re-evaluate the new bin set with regard to the wastage. Based on this iterative step, we can add some new bins and remove some existing bins and finally come up with a new bin set that reduces the wastage. We have done this in cooperation with a company and found that we can reduce the wastage by more than 1 percentage point. Our algorithm can also be applied to identify eco-efficient cutting layouts and to identify them very fast. And this is necessary in order to automatize the step of cutting rings from rectangular bins. Finally, we can use our algorithm to identify which of the so far wasted material should be stored for future jobs. Thank you very much for your attention and feel free to ask some questions. Thanks.